Welcome dear students. Welcome to the lecture series on electromagnetic field theory. This is tutorial number 1. So before starting this tutorial, I wanted to talk to you guys because I felt like something which I wanted to share with you. You see, most students make mistakes in MCQ and end up losing marks via negative marking. But here is the twist. Most students blame their IQ, but the real problem is understanding the original core concept. Usually students think that they are not able to memorize a lot of concept, they are not able to memorize the formula, or not able to understand the concept properly, or they make mistakes via calculation mistakes. But the problem is not that. The problem is understanding the original core concept, which cannot be gained by reading just one book, or maybe the teacher has not explained that in the classroom setup. You see, I have spent 6+ years in the field of electromagnetic field theory. I have read more than 10 books, 10 different textbooks from different authors, understanding the same concept again and again. I have published various research papers in national as well as international conferences. And I have understood that in order to solve a multiple choice question, you need to understand not just the correct answer, but also the incorrect answers, the psychology behind the incorrect answers. You see, when the IT professor frames a question, he understands that what a student can make mistake, where a student can make mistake, right? So the questions are framed in such a way that the students are usually tempted towards choosing a incorrect option. So it is very important to understand not just the correct answer, but also the incorrect answer. So in this tutorial, you will see multiple ways of solving a question, multiple approach of solving the same question, and you will understand all the options, including correct as well as incorrect answers, which will help you to boost your confidence. Okay, my name is Biplab. I am a PhD research scholar at IIT Kharagpur, and I will help you to understand 5 different multiple choice questions in this tutorial, out of which I have solved 4, and I will give 1 question as a homework to you. I hope that will be helpful for you. Okay, so let's start the tutorial.
Alright, so let's start tutorial number 1, electromagnetic field theory. So in this tutorial, these 3 concepts are mainly covered. All the MCQs are based on these 3 concepts only. So let's start with the MCQs. So the first question says, which of the following is known as equation of continuity? So there are 4 options. Now if you carefully look at all these 4 options, you will be able to figure out few minor details. First is that, let me choose a different color. Okay, this is a field quantity J. This is a circuit quantity psi E. This is also a field quantity D. This is also a field quantity B. This is also a field quantity E. This is a field quantity B. Okay, and this also is a field quantity. Actually it's a charge, so we can call it circuit quantity QV. Okay, so if you see in this equation, these are some of the important point that you should notice. Next thing that you should notice is that there is a differential operator del, and there is integral operator, and there is partial derivative with respect to time. Okay, and also there is j omega term present. All right, okay, so these 3 field quantities are written in scripted form. So these three set of quantities are instantaneous field quantities. Okay, these two they are circuit quantities. And these two they are complex field quantities. Okay, so there are three different sets of quantities which are given in this question. This first set is field quantities, but they are in instantaneous form. This set is also a field quantity, but it is in complex form. Okay, that is why they are written in Roman letter E and B, where if you see here, this B letter is a scripted form. It is written in scripted form like this. The J is written like this. The D is written like this. So these are written in scripted form. That is why they represent instantaneous field quantities. Whereas these two quantities are circuit quantities. They are not field quantities. Okay. Now, here we have a divergence operator del. We also have a double integral. We have a partial derivative with respect to time, and we also have j omega. So all these things constitute these four options. Alright, now let us look at all the different forms of Maxwell's equation. So I have written all the forms of Maxwell's equation in one table. If you see these four set of equations, 1, 2, 3 and 4, here del operator is used. Scripted letters are used like E, H, B, J and D. Okay, and partial derivative with respect to time is also used. So that is why these four set of Maxwell's equation is called Maxwell's equation written in differential form for instantaneous field quantities. Instantaneous field quantities. Why differential form? Because the del operator is present. Why instantaneous field quantities? Because all the fields are written in scripted form. That is why instantaneous field quantities. Okay, that is why these four set of Maxwell's equation is called differential form Maxwell's equation written for instantaneous field quantities. Okay, on the other hand, if you see these four set of equations, here integral operator is present. Also instantaneous field quantities like E, H, B, D, all these field quantities are written in scripted form. So they represent instantaneous field quantities, and all these Maxwell's equation are called Maxwell's equation written in integral form. Integral form for instantaneous field quantities. Okay, if you see these four set of equations, here integral operator is present, field quantities such as E, H, B are present, and circuit quantities such as psi E, I and Q, they are also present. So these set of Maxwell's equation are called mixed Maxwell's equation or mixed form Maxwell's equation. Okay, if you see these four set of equations, okay, why these are called mixed form Maxwell's equation? Because both field quantities and circuit quantities are present in the same Maxwell's equation. That is why they are called mixed form. Okay, because of the presence of both the field quantities E, H, B as well as the circuit quantities psi E, current I and charge Q. Okay, that is why they are called mixed form. Alright, let's move on to the next set. Here if you see, all the quantities are circuit quantities like V, U, I, psi E, psi. Okay, here also psi Q. So we have summation, we have normal derivative, and we have circuit quantities such as U, V, U, I, Q, psi and psi E. Psi E is called electric flux, whereas psi is magnetic flux. This is charge Q, this is current I, this is magnetomotive force U, and this is voltage V. Okay, if you see carefully, in the integral form also, in the integral form, this partial derivative del by del t has been changed to the normal derivative d by dt. So this is also one thing that you should write here, that it contains normal derivative d by dt. It's not a partial derivative. Whenever it's a partial derivative, it's in differential form. Whenever it's a normal derivative, it's in integral form. Okay, so here also this is a normal derivative, and summation signs are used because of this closed cyclic integral has been converted to the simple summation. Alright, so now here these four set of Maxwell's equation, they are called Maxwell's equation written in purely circuit form. Alright, okay. Now if you see these four set of equations, here we have used Roman letter E, H, B, and J omega term is also used. Okay, so that is why these are Maxwell's equation written in complex form. Okay, alright, so now you have understood that a Maxwell's equation can be written in various forms. Now if you check these four options, you will notice that option number C is in differential form for instantaneous field quantities, and it's a Maxwell's equation. This one, this is Gauss law for magnetostatics. Okay, if you see this D, option D, this is also Maxwell's equation written in complex form, this particular equation, which is Maxwell-Faraday law written in complex form. Okay, so C and D are Maxwell's equation. You have been asked to find the equation of continuity. So C and D are Maxwell's equation, they are not equation of continuity. So only two options are left, A and B. So now let's see our next thing. These five set of equations, they are called equation of continuity. Continuity. And they are also called conservation of charge equation. Conservation of charge. Okay, so this first option, del dot J is equal to minus del by del T of QV, which is this particular equation, is called equation of continuity or conservation of charge. Okay, if you see that this equation can also be written in different forms, like this first one is written in differential form, this is written in integral form, this is written in mixed form, this one is in circuit form, and this is in complex form. Okay, now if you see this option number B, Option number B is a relationship between circuit quantity psi and field quantity D. Okay, now let us look these four quantities. Here, if you see carefully that the circuit quantity V, I, Q, psi, psi E and U, these are all circuit quantities. Whereas E, J, B, D, H, these are field quantities. Okay, so these 6 set of equations, they are known as relationship between, this tells us the relationship between circuit quantity and field quantity. Okay, so this option number B is actually a relationship between circuit quantity psi E and field quantity D. Okay, so in this question you have been asked to find that which of the following is known as equation of continuity. So the correct answer is option number A. A is the correct answer, which is equation of continuity. Okay, but you have also understood what is equation number, what is option number B, what is option number C, and what is option number D. You know the thorough full knowledge about all these 4 options. This was the objective of solving this first equation. Not just knowing the correct answer, but you also know in very detail the wrong answers also. Okay, all right. Now let us look at the second equation. Which of the following is or are not a Maxwell's equation? So this time it will be easy for you. There are 4 options, A, B, C and D. This first one is Ampere's law. This second one is equation of continuity. This third one is just a relationship between circuit quantity and field quantity. And this fourth one is this is a del cross H, J omega D plus J. So this is a Ampere's law, Ampere's circuital law. Okay, so it has been asked that which of the following is or are not a Maxwell's equation. So this first one is a Maxwell's equation. This is a Maxwell's equation written in integral form. And also you can say that it's a Maxwell's equation written in mixed form, because both the circuit quantities and the field quantities are present. So it's a Maxwell's equation written in mixed form. So this is a Maxwell's equation. This fourth one is also Ampere's circuital law. This is written in complex form. Why? Because the fields H, D and J, these are written in Roman letters. Okay, so this is also a Maxwell's equation. Option number B is just we saw in the first question that it is equation of continuity or conservation of charge. So this is equation of continuity. And C, option number C is relationship between circuit quantity and field quantity. So you have been asked to find which of the following is or are not a Maxwell's equation. So the correct option is option B and option C. Both these options are not Maxwell's equation. Okay, A and D are Maxwell's equation, but B and C are not. Okay. So question number 3 says, consider the following statements. The first statement is, motion of magnetic dipoles in a ferromagnetic material constitutes magnetic displacement current. Statement number 2 is, Maxwell's equations are asymmetric. And statement number 3 is, total current in a circuit is always solenoidal. Which of the following statements is or are correct? So let's look at each of these statements one by one in full detail. So the first statement is saying that motion of magnetic dipoles in a ferromagnetic material constitutes magnetic displacement current. So this is a question which is based on generalized current concept, where you should know few things about materials. The first is, we have a conductor which is a material. Second material which we normally deal with is a dielectric material, and third one is a magnetic material or magnetic core. Okay, so these are the three main types of materials which we normally deal with in case of a while studying electromagnetic field theory. Now in conductor we usually have free electrons. Okay, that we already know, we have free electrons. So these are free charges which are free to move. That is why they constitute conduction current density, Jc. Whereas in dielectric we do not have free electrons, we have bound charges. When I say bound charges, means plus and minus together they make a electric dipole, and these small dipoles, they are called bound charges. So let us consider a small bar of dielectric where there are lot of bound charges present. Okay, like this. Usually they are not aligned in a same manner, they are rotated in different fashions. Okay, so these bound charges, when they tend to move in the vicinity of an electric field, they constitute a type of charge which is called displacement current. Okay, since this is happening in a dielectric and these bound charges are electric charges, that is why we call it electric displacement current. Electric displacement current. Okay, in third case, where we have a magnetic material such as a ferromagnetic material, in the statement it has been given that the magnetic motion of magnetic dipoles in a ferromagnetic material. So in a ferromagnetic material, again we have bound charges, that is plus and minus, but these are magnetic charges, magnetic dipoles, or in other words you can call it. So again plus minus, plus minus, plus minus. These are magnetic dipoles, and these magnetic dipoles, when they tend to move, they constitute magnetic displacement current because they are not free charges, they are bound charges. So when the bound charges move, they constitute displacement current, and since this is happening inside a magnetic core and these bound charges are magnetic dipoles, therefore it is called as magnetic displacement current. Okay, so the first statement, motion of magnetic dipoles in a ferromagnetic material constitute magnetic displacement current, this is a correct statement. Let's see statement number 2. Maxwell's equations are asymmetric. Now if you see a Maxwell's equation, let me remove this part. Okay, let us write the Maxwell's equation one by one. The first is del cross E is equals to minus delta B over delta T. Del cross H is equals to delta D over delta T plus JC, and here we have del dot B equals to 0 and del dot D is equals to QV. Okay. Now, by looking at these four equations, one can easily be confused and say that the Maxwell's equations are actually asymmetric, but actually they are not asymmetric, they are symmetric. But you need to understand why they are symmetric. In the statement it has been given that the Maxwell's equations are asymmetric. This is totally a wrong statement. Maxwell's equations are always symmetric, but looking at these four equations, one can easily get confused that the Maxwell's equations are asymmetric. Why? Because if you see here in these two curl equations, del cross E and del cross H, the right hand side here has only one term, whereas right hand side here has two terms. Here the right hand side is 0, here the right hand side is QV, right? So one can easily get confused. But why is it that so that the equations look asymmetric but the Maxwell's equations are actually symmetric in nature? So let us see why. Because of the reason that inside a magnetic core, so here we have a magnetic core, let us call it a simple magnet. A simple magnet has a north pole and a south pole, right? So these dipoles, these bound charges when I was talking about, these were actually north pole and south pole. This is actually the better representation of showing the magnetic dipoles rather than showing plus and minus signs. Okay, so north pole and south pole, they together will constitute a magnetic dipole. This is the correct representation. So let us come back to our second statement. Let us suppose we have a magnetic bar which has a north pole and a south pole, and if you say that I will break this jar from the middle, and if you break it and if you make it apart like this, do you think that you will get a single north pole here and a single south pole here? This is never possible, because the moment you break this, again a dipole will be formed, a small dipole where it will have a small north, small s, north and s. So a magnetic monopole is never possible. Okay, because of the absence of magnetic monopole, we do not have free charges present inside a magnetic core or a magnetic material. Like in case of a conductor, we have free electrons, right? But in case of a magnetic core, you cannot have free charges. Like you cannot have only a north pole moving around anywhere. You cannot have that situation. Okay, because of this reason, the magnetic conduction current M superscript C, this is an impossible case. This is not possible in case of a magnet. That is why here M subscript C is not present. Okay, this is why this del dot B is also equals to 0, because when you see equation of continuity, you know that del dot J is equals to minus d by dt of QV, right? So if in case of a magnet, this del dot M subscript C is equals to minus d by dt, this is a completely incorrect statement or incorrect equation. Why? Because the conduction magnetic current does not exist, which also means that magnetic charges QV is also not possible. That is why in this equation del dot B, the right hand side is 0, because QV in case of a magnet is not possible. In case of electric, it is quite possible. It is always possible. That is why del dot D is QV, but del dot B is 0. Understood? So this is the only reason why the Maxwell's equation looks asymmetric, but in reality Maxwell's equations are always symmetric. Okay, so equation number 2 is incorrect. Now what's equation number statement number 3 is saying? Statement number 3 says total current in a circuit is always solenoidal. Okay, let me rub all this so that I get some space. Okay, all right. Now you know that del cross E is equals to minus delta B over delta T. If you add a source, a magnetic source, MI, magnetic current, then this can be written as minus MT, where this is the total magnetic current. Similarly, the curl operation with magnetic field, that is del cross H, is equals to del D over del T plus JC plus JI. I am adding this term extra because of the impressed current, that is the source current. If you want to have a look at where these equations from where I am adding this term, you should watch lecture number 2, which is Generalized Current Concept, where I have covered these things in every detail. So all these 3 terms will make it JT. Okay, where JT is the total electric current density. Okay, so the superscript T stands for total. So MT is total magnetic current and JT is total electric current. Okay, so these are densities, magnetic current density and electric current density. Now according to a vector identity, we know that when we take divergence of any vector A, it is always 0. We call it divergence of a curl is always 0, DC. Similarly, a curl of a gradient is also 0. That is, when you take a curl of a gradient of any vector A, it is always 0. We call it curl of a gradient is 0. These are 2 vector quantities which we study in vector concepts. Okay, now if you take divergence of this first curl equation, that is, you take the divergence of this. In the right hand side also you have total magnetic current MT. So you have taken divergence in the both side, left hand side as well as right hand side. But according to this identity, this right hand side will go to 0, which means that divergence of total magnetic current is 0. Similarly, if you take the divergence for the second Maxwell's equation, which is del cross H, you take the divergence, it will become divergence of J total. Similarly, the left hand side becomes 0, so divergence of JT is 0. So whenever the divergence of any vector is 0, we call that vector is solenoidal. Okay, solenoidal. And whenever the curl of any vector is 0, we call it irrotational. Okay, so in this case we are getting divergence of MT and divergence of JT, both are 0, which means the total magnetic current and total electric current is solenoidal. And the third statement says that the total current in a circuit is always solenoidal. So statement number 3 is also correct. So if you see these options, statement number 1 and 3 is correct. So option number D is the correct option. Okay, so this is a correct option. Alright, so now let's move on to the next question. So this question says, consider a non-magnetic metal X given J is equals to 50 milliampere per meter square and electric field E is equals to 10 microvolt per meter. Determine admittivity and conductivity of the metal at 9 gigahertz respectively. So in these options, it is given equal to 5 kilo Siemens per meter. So this first is admittivity and second one is conductivity. It has been asked to determine admittivity and conductivity of the material. So let's start the solution. So before starting, let us look at what is admittivity and conductivity. So the admittivity of a material is given by the relation y cap, which is a function of omega, is equals to sigma cap plus j omega epsilon cap, where this sigma and epsilon are complex conductivity and complex permittivity of the medium, and y cap omega is complex admittivity of the medium. Similarly, z cap is complex impedivity of the medium. This is admittance and this is impedance. So z cap is complex impedivity of the medium and mu cap is complex permeability of the medium. So these two equations will be used in this question. Basically in this question you have been asked to find the complex admittivity, that is y cap, and the conductivity, which is sigma cap. So this first equation is going to be used in this equation. Now how is epsilon cap, mu cap and sigma cap written? So epsilon cap is epsilon plus epsilon 1 del by del t plus epsilon 2 del square by del t square plus dash dash dash, all other higher order terms of derivatives of with respect to time, which can also be written in complex form, where this derivative term is changes to j omega. Here two derivatives are present, del square by del 2 square, so j omega whole square is equals to minus omega square. That is why we have minus omega square present over here. Similarly, mu cap is also given by this relation and sigma cap is given by this relation. So one may say that we have never seen equations of permittivity, permeability and conductivity in this form. We have not seen it because in the normal standard textbook, usually what is given is the permittivity and permeability of free space, okay, which is valid only for free space, and matter which is a linear matter and seen in a simple sense. But in general, when you see a matter which is linear in nature but not in simple sense, then the permittivity and permeability equations look something like this. Okay, why this is happening? The reason is what we saw in question number 3, where we have seen that the bound charges were present in the dielectric material, right? Bound charges were present. Usually electric field does not always move in a straight line. So let us say electric field changes with respect to time very fast, but since these bound charges plus and minus, they have some mass, so it takes for them to get aligned with the electric charges. So there is a delay present in between that. Because of that delay, you cannot take the assumption that the derivative with respect to the electric field is always negligible. Okay, the equations that we usually see is D is equal to epsilon E. While in reality, this epsilon is epsilon cap, which is this whole relation. Okay, the questions that you know is D is equal to epsilon E, which is alright, but it is okay for linear matter which is seen in simple sense. Simple sense. When I say simple sense, means the electric field is not changing with time at a very fast rate. So that is why these derivative terms, they are neglected, and you are left out with only this simple epsilon or the simple mu. Okay, so this is the half truth which you know and which are usually given in textbook for undergraduate students, but the full reality is this. All right, so let's see what has been asked in the question. Now if you see here, for free space, sigma cap is 0, epsilon cap becomes epsilon naught, which is free space permittivity, and mu cap becomes mu naught, which is free space permeability. That is why the admittance becomes j omega epsilon cap and impedance becomes j omega mu cap. For non-magnetic metal, which is asked in this question, see, this sigma cap becomes sigma, epsilon caps become epsilon naught, and mu cap becomes mu naught. For non-magnetic dielectric, sigma cap is 0, epsilon cap remains epsilon cap, and mu cap is mu naught. So the admittivity and impedivity of the medium is these two equations. For ferromagnetic material, sigma's cap is sigma, epsilon cap and mu cap remains like that. So the admittivity and impedivity for ferromagnetic material is like this. Okay, so this is one chart which you should keep in your notes, which will be very helpful while solving questions related to generalized current concepts and impedivity and admittivity of the medium. Now in this question you have been told that you have a non-magnetic metal and you have to find the admittivity y cap and the conductivity sigma. Okay, so now let's start this simple solution. So we know that J is equal to sigma cap plus j omega epsilon cap E, which is also written as y cap, which is a function of omega times E. So y cap, which is a function of omega, can be written as j over E, and j is given as 50 milli, and electric field is given as 10 micro. So it becomes 5 into 10 to the power 3. The units of J is ampere per meter square, and the units of E is volts per meter. So this becomes 5 into 10 to the power 3 ampere per meter square into meter per volts. So 1 meter cancels out. So you are left out with ampere per volt meter. So ampere per volt can be written as Siemens per meter. So the correct answer is 5 into 10 to the power 3 Siemens per meter, or 5 kilo Siemens per meter. Okay, so the answer for admittivity, you have got it as 5 kilo Siemens per meter. Now you have been asked to find the conductivity of the medium at 9 gigahertz. Okay, so let's write this equation once again. Y cap omega is equals to sigma cap plus j omega epsilon cap. So for a non-magnetic metal, we know that this sigma cap is replaced by sigma and this epsilon cap is replaced by epsilon naught. So let's write it once again. Sigma plus j omega epsilon naught, sigma plus j omega is 2 pi f. F is given as 9 gigahertz. So 9 into 10 to the power 9 into epsilon naught. The value of epsilon is 1 over 36 pi into 10 to the power minus 9. So plus 9 and minus 9 cancels out, and you are left out with sigma plus 0.25 divided by pi, and j is also present. So this is y cap. Okay, so this y cap you have found it here, so you can replace it here. You can just write 5 into 10 to the power 3. Now since we know that this sigma cap was a function of omega, but since for a non-magnetic metal this sigma cap becomes sigma, therefore we can say that initially when sigma cap was sigma plus j omega sigma 1 minus omega square sigma 2, all these terms are not present here, they are neglected for non-magnetic metal. So you are only left out with the real part. The complex parts j, all these terms are gone. So sigma is just a real number. So this is a real number, and this second part is a imaginary part. Okay, so we can find out the what I can say the magnitude of this part, so which is under root of sigma square plus 0.25 over pi whole square. This is 5 into 10 to the power 3. So if you take square on both sides, you will get 5 into 10 to the power 3 whole square is equals to sigma square plus 0.25 divided by pi whole square. So if you solve this, you get sigma is equals to under root of 5 into 10 to the power 3 whole square minus 0.25 divided by pi whole square, which is equals to 4999.99 Siemens per meter, which is nearly equal to 5 kilo Siemens per meter. This is not exactly equal, this is nearly equal to 5 kilo Siemens per meter. Okay, so now if you see and check the options, the admittivity is exactly equal to 5 kilo Siemens, right? But the conductivity is nearly equal to 5 kilo Siemens per meter. So option A is the correct option. Okay, now one may say that what is the need of doing all these calculations? Simply, if a smart student will not try to solve all this, he will just solve this simple part, and you can directly say that y cap becomes 5 kilo Siemens per meter, which is exactly equal to 5 kilo Siemens per meter. But since y cap is equals to sigma plus j omega epsilon, that means y cap is a summation of two terms, which simply means that sigma should be less than 5 kilo Siemens per meter. Alright, it cannot be exactly equal to 5. That is why just by calculating the first part, you can directly tell that option number A is the correct option. Okay, so option A is this one is the correct option. Alright, okay.
Okay, this is question number 5. I'm going to give this question to you as a homework. So please try this question and try to give me the answers in the comment box. So let me read this question to you. The question says electric field is incident on a magnetic core with large mu. If the induced current in the core is 3 microampere per meter square and the electric field is E is equals to 2 AX cap plus K AZ AY cap microvolt per meter. Consider the source free case. Determine the value of K, the type of induced current and the direction of current is. Okay, so you need to find the value of K. So K is here in the expression of electric field, and you also have to find out the
type of the induced current and the direction of the current. So in this question, the electric field is incident on a magnetic core, and when the electric field is incident on a magnetic core, it induces some current in the core. You need to find the type of that induced current. So the current can be a magnetic displacement current, it can be electric displacement current. Okay, you also need to find the value of K. So there are different values of K here, 3, 2, etc. And you also have to find the direction of the current. Okay, so let me give you a hint. So in this question, you know that del cross E is equals to minus delta B over delta T plus Mi, which is equals to minus Mt. So this is the total magnetic current. This is the source magnetic current Mi, but in this question it has been given that consider source free case. So you can assume or you can neglect this term. So the only term which is left is delta B over delta T. So if you know what is this term called, then you can easily tell that which type of current has been induced in the magnetic core. Okay, so the only thing which is left out is to find out the cross product of del operator and the electric field. Okay, and here the del operator with the electric field can be easily found, like del cross E is equals to Ax cap, Ay cap, Az cap, del by del x, del by del y, del by del z. This first term of electric field will be electric field in the x direction, electric field in y direction, and electric field in z direction. So if you solve this and equate this to delta B over delta T, then you can find the value of K. Okay, so I hope you will be able to solve this question. You have to find out the value of K, the type of the displacement current, and the direction of the current. Okay, alright, so please try this at your home and write me in the comment box your options, and if you have any doubts, please write it in the comment box so that I can see and try to answer all your questions. And I will be very much happy if you subscribe this channel, because it gives me a lot of motivation. So thank you for watching this tutorial. I hope this was helpful for you. Thank you.